Welcome to the class on artificial neural networks. In this video, we start with supervised learning and we look at classification as a geometric problem. So we have an input, for example, some image, which goes into a classifier. That could be a neural network, that could be something else. And then we want the classification. And for the moment, it's just binary. Either it's a car, yes or no. Just a single output, yes or no. Now, more generally, we can think of an input vector, and then we use the classifier. And the classifier, if it's a neural network, if it's something else, in any case, it will implement a nonlinear function f of x. It transforms an input vector into an output. And now we want an output of +1 if it's a car and 0 if it's not a car. So what I would like just to, as a background, to give you the intuition is this transformation from images to vectors. Suppose we have here some image, and let's take not a car, but let's take a house. And then this is really a pixel image. So we would have maybe 128 lines, 128 columns. So it would be 128 times 128 image, which means in total I have in the range of 16,000 pixels. And let's for the moment just take black and white, so we don't have to worry about color. And now the idea is that we take the first row and put it here. Then we take the second row and put it next to it. And then we take the third row and put it next to it. And so in the end, we take all these different rows and define this then as a vector x. And now this vector x is in this pixel space. So it has 16,000 components. Now, why do I say this? I say this because if we do this, then the two-dimensional order of pixels is neglected. So the two-dimensional order that we have here that really makes the image is completely neglected. And for most of the class, that's how we do it. We forget that we could start with images. We always work with input vectors. And now we have one of these vectors. Say I have a vector x, which has components x1, x2, and so far xn. So this index here is the index of the component of this vector. Now, this would be one image, say a house, and we will have different images of cars that belong to the class, and then we have different images of non-cars, such as houses. So what I say is that each image is one vector, and then I have another index mu, and this is the index of the pattern. So the first pattern could be a car, the second pattern could be a house, the third pattern could be a car, the fourth a car, and so forth. And so now we draw these vectors. I cannot draw in this 16,000 dimensional space, but I can pick out 3 arbitrary components. Say I pick out component x1, I pick out component x17, I can pick out component 156. These are randomly picked indices. And now we have these examples of cars, and these are vectors that lie in this high dimensional space. And then we have vectors that correspond not to cars, say to houses, to trees, to streets, to birds, and these are also vectors. And it's because they are not belonging to the class, I denote them as just red circles, different color, different shape. And now the point I would like to make is the following. Classification amounts to finding a separating surface that puts apart the blue positive crosses from the negative examples from the red points. So this surface could look like this, that I have here sort of some surface, and now the idea is that all these blue points lie on the positive side of this surface, and all these red points lie on the negative side. They lie below this surface. And so the task of classification is now equivalent to finding this separating surface which is really this green separating surface here. And once we have this separating surface, we are done with the problem of classification. So we go from images to vectors, and then we go from vectors to classification. And if I don't make a two-dimensional image, but if I don't make a three-dimensional image, but if I just pick two components, then I have different examples. The different cars are the positive examples. Then I have the non-cars, which are the negative examples. So I will have many of these positive and negative examples. And then the task of classification is to find this separating surface. And if I plot this in 1D, then if I plot this in 2 dimensions, then the separating surface is just one-dimensional. So let me summarize this. The task of classification is to find a separating surface in this high-dimensional input space. Remember, it's even with 128 times 128 pixel images, the dimensionality of the input is 16,000 or more. Now, how could we define this separating surface? We can say the separating surface corresponds to a discriminant function, and the discriminant function is called d of x, and this discriminant function is 0 on the surface, and then it's positive for all the positive examples that lie above the surface, and it's negative for all the counter examples that lie below the surface. So defining or finding the surface means finding a discriminant function so that the positive examples give a positive value and that the negative examples give a negative value, and then we are done. The separating surface is the set of all points where this d of x is exactly 0. Now, a particularly simple case would be the linearly separable problem. Linearly separable means that this separating surface can be described by just a linear function.